Have you ever rubbed a balloon on your hair and then watched it just stick to the wall? Like, defying gravity.
Oh, yeah. Classic demo.
Or, seeing a huge lightning bolt flash across the sky. It feels almost like magic, but it's not.
Not at all. It's physics.
Exactly. And that's what we're diving into today in our Simple Science Summary. We're tackling electrostatics, basically, the science of stationary electric charges and how they interact.
Huh?
We're focusing on the core ideas you'll find in the CFPS document, stuff that's really key for your NSC examination. The goal is to break it down, make it click.
And it's so important, isn't it? Not just for exams, though obviously, yes, crucial for those grade 12 papers.
Right.
But it's fundamental. So much technology relies on these principles. Think about photocopiers or even the touch screen on your phone.
Really? Even touch screens?
Absolutely. Understanding electrostatics helps demystify all that. It takes it from feeling like, magic to actual understandable science. I remember in the lab once with a Van de Graaff generator.
Oh, those things.
Yeah. Suddenly, everyone's hair is standing on end. That's that invisible force, the electric field, just making itself very, very obvious.
That's a perfect picture.
Mm-hmm.
Okay, so let's start right at the beginning then. What exactly is electric charge? We talk about positive, negative, neutral.
Right. So fundamentally, charge is just a basic property of matter, like mass. You've got positive charges, usually protons stuck in the atom's nucleus, and negative charges, the electrons whizzing around.
And neutral, does that mean no charge?
Good question. Neutral doesn't mean zero charge. It just means a perfect balance. Equal amounts of positive and negative charge, so overall they cancel each other out. Most things around us are neutral most of the time.
Okay, so it's all about balance. It's when electrons move that things get interesting, right? Losing electrons makes something positive. Gaining makes it negative.
Exactly. Those little electrons are the mobile ones. They're the key players in charge transfer.
And that brings us to a really big rule, doesn't it? The law of conservation of charge. You mentioned charge transfer. Does this law mean charge itself can't just be, made or destroyed?
Precisely. That's one of the fundamental laws of the universe. Charge isn't created. It isn't destroyed. It just moves around. It gets transferred from one object to another.
Okay.
Think of it like money. You can move it between accounts, but the total amount stays the same unless you get an external deposit or withdrawal, which doesn't happen with charge in a closed system. It's conserved.
A cosmic accounting ledger. Always balanced. I like that. So how does this play out practically? Say you have two charged spheres.
Okay, let's picture it. Imagine sphere A has, say, +5 coulombs of charge.
+5, got it.
And sphere B has netted to 7 coulombs. Lots of extra electrons there.
Okay, -7.
Before they touch, the total charge in this little system is +5 plus -7, which is
-2 coulombs overall.
right. Now bring them together so they touch. They have to be conductive, of course.
Right, so charge can move.
Yes. The electrons, being mobile, will immediately redistribute. They'll flow from where there's an excess, sphere B, to where there's a deficit, sphere A, trying to balance things out.
Like water finding its own level.
Kind of, yeah. It's seeking equilibrium. So this electron migration happens, and then you pull the spheres apart again.
Okay, what happens though?
That total charge, the -2 coulombs we calculated, is still the total charge of the system. Conservation holds. But now, because they touched and redistributed, that charge gets shared equally between the two identical spheres.
Equally. So each one gets...
-1 coulomb each.
Okay. So the total is still -2, but it's spread out. +5 and -7 became -1 and -1.
Exactly. And that basic principle explains so much, like charging by contact, static buildup, that shock you get from a doorknob sometimes.
Right, that little zap. So
Right.
that's just electrons jumping to find balance.
Millions of them, yes.
Yeah.
Suddenly equalizing the potential difference. And, being able to calculate the number of electrons transferred, which is something you'll do for the NSC, that really drives home the point. It shows it's not just some vague static, it's a quantifiable movement of discrete particles, these electrons. Makes it less mysterious.
Definitely less mysterious. Okay, so charges exist. They move around, but are conserved. How do they actually interact? How does one charge feel another one across space? That's where Coulomb comes in, isn't it?
Yes, Charles Augustin de Coulomb. He figured out the mathematics of that invisible push-or-pull, Coulomb's law.
And what does it state, basically?
Essentially, it says the force between 2-point charges is directly proportional to the product of the charges. Bigger charges mean a bigger force.
Makes sense.
And here's the really crucial part. It's inversely proportional to the square of the distance between their centers.
The square. Okay, so distance is a big deal.
A huge deal. Double the distance, and the force doesn't just halve, it drops to a quarter of what it was. It falls off really quickly.
You know, that sounds so much like Newton's law of gravitation back in mechanics.
It is. It's striking, isn't it? Both are inverse square laws. It suggests a fundamental way forces work in the universe, whether it's gravity acting between masses or the electric force acting between charges. They both seem to operate through some kind of field, and the influence drops off with the square of the distance. It's not just a random formula, it reflects something deep about how interactions happen.
That connection really helps make sense of why it's an inverse square law.
Right.
Okay, so practically, for the NSC exams, how do we apply Coulomb's law?
Right. Application. You'll mostly see it in two main scenarios. First, calculating the net force in one dimension, like 3 charges all lined up.
Heck, 1D.
And second, calculating force in 2 dimensions, but specifically limited to 3 charges in a right-angled arrangement. Usually you'll find the net force on the chart is sitting at the 90-degree corner.
Okay, so vector addition will be important there, finding the resultant force.
Exactly. You'll need your vector skills.
Now, speaking of calculations, I remember a really important tip about using the formula. Something about the signs of the charges. You're not supposed to just plug in the plus or minus signs.
Yes, absolutely critical tip. Please remember this one. It catches so many people out.
Why is that? What goes wrong?
Well, the signs, positive or negative, tell you the direction of the force. Like charges repel, unlike charges attract. That's direction. If you put the signs into the F equals K, Q1, Q2 over R squared formula, you might get a negative answer for the force magnitude. And then trying to combine that negative magnitude with directions when you have multiple forces becomes incredibly confusing.
Okay, so what's the foolproof method?
Right. The foolproof method is step 1, use the magnitudes, the absolute values, just the numbers, of the charges in the formula to find the size of the force. How strong is it?
Okay, get the strengths first.
Step 2, look at the charges. Are they the same sign or different? Determine the direction. Is it attraction or repulsion? Draw it. A little free body diagram showing the forces acting on the charge you care about is essential.
Draw the picture. Always good advice.
Always. Then, step 3, choose a positive direction for your calculation, like to the right is positive. Finally, add up the forces like vectors, using positive for forces in your chosen direction and negative for forces in the opposite direction. Handle the direction conceptually after calculating the magnitude.
Got it. Magnitude first, then direction using attraction repulsion, then vector addition with the chosen positive direction. That seems much clearer.
It avoids so many common mistakes, honestly.
So let's just reinforce that sensitivity. If I double one charge, the force.
Doubles. Direct relationship.
And if I double the distance between them?
Force drops to 1/4. That inverse square relationship really bites.
Wow, okay, distance is king there.
Definitely. And you'll see this graphically, too. Force versus product of charges gives you a straight line.
Okay.
Force versus distance, that's a sharp downward curve.
The inverse curve.
Exactly. But if you plot force versus 1 over distance squared,
now then you get
a straight line again. Because the force is directly proportional to 1 over r squared. Seeing those graphs helps solidify that inverse square idea, and they do pop up in exams.
Makes sense. Okay, we've talked about the force between charges, but what about the space around a charge? Does the charge change the space itself? This idea of an electric field.
Yes, the electric field. It's a really powerful concept. It's basically a region of space around a charge or a group of charges where another charge would experience an electrostatic force if you placed it there.
So it's like an influence zone.
Exactly, an influence zone. And to define the direction of the field at any point, we use a little hypothetical tool, the positive test charge.
The imaginary +1 Coulomb guy.
That's the one. It's purely theoretical, +1 Coulomb. The direction the electric field points at any location is simply the direction that tiny positive test charge would be pushed or pulled if it were placed right there.
So the field shows the direction of force on a positive charge.
Precisely. It helps us map the influence.
And how do we visualize these fields? You mentioned field lines earlier.
Right, electric field lines. They're the standard way to draw these invisible fields. They have rules you need to know.
Okay, what are the key rules?
1, they always start on a positive charge and end on the negative charge or go off to infinity. And they always leave or enter the surface of a conductor perpendicularly at 90 degrees.
Perpendicularly.
2, critically, field lines never cross each other.
Why not?
Because if they crossed, it would mean at that single point, the field points in 2 different directions. A test charge can't be pushed in 2 directions at once, so no crossing.
Makes sense. One direction only at any point.
3, Arrows on the lines show the direction always away from positive, always towards negative. Remember, it's the direction a positive test charge would move.
Away from positive towards negative.
Got it.
4. How close together the lines are tells you the field strength. Closer lines mean a stronger field, more force. Lines spread further apart mean a weaker field.
Density equals strength. You got it. And lastly, the number of lines drawn starting or ending on a charge is generally proportional to the magnitude of the charge. More lines for a bigger charge.
Okay, those rules give us a language to draw fields. What do some common patterns look like? A single positive charge.
Radiating outwards, like spokes on a wheel, arrows pointing out.
Single negatives.
Radiating inwards, arrows pointing in.
2 positive charges near each other.
The lines would look like they're pushing away from each other, curving outwards between the charges, showing repulsion.
And a positive and a negative charge. The classic dipole.
Ah, that's the nice one. Lines elegantly curve from the positive charge and swoop into the negative charge. You can almost see the path a test charge would follow.
Cool. What about parallel plates, like in a capacitor?
That's a really important one. Between the plates, away from the edges, the field lines are straight, parallel, and equally spaced.
Meaning
The electric field is uniform in that region. Same strength, same direction, everywhere between the plates. Very useful.
Okay, uniform field between parallel plates, good to know. Now, how do we quantify the field? We talked about strength.
Yes. Electric field strength, often just called the electric field, symbol E, it's defined as the electrostatic force experienced per unit positive charge placed at that point.
Force per unit charge. So there's a formula connecting force, field, and charge.
There is. E equals F over Q. Electric field strength is force divided by the test charge experiencing that force. Or, rearranging the source on a charge Q in a field, E is F equals E times Q.
F equals EQ,
Yeah.
okay? And E is a vector, right, like force.
Absolutely. Direction matters. The direction of E is the direction of the force on a positive charge. If you put a negative charge in the field, the force on it will be in the opposite direction to the field lines.
Right, opposite direction for negative charges.
Yeah.
And can we calculate the field caused by a point charge itself?
Yes, there's another key formula for that. E equals KQ over R squared, where Q is the charge creating the field and R is the distance from that charge to the point where you're calculating the field.
E equals KQ over R squared. Looks similar to Coulomb's force law.
It is. It's basically the force per unit charge, so one of the Q's from the force law disappears.
Ah, I see. And if you have multiple charges creating a field,
You use superposition, just like with forces. Calculate the electric field vector due to each individual charge at the point you're interested in.
using E equals KQ over R squared for each one.
Right. And then you add those individual electric field vectors together, head to tail or using components, to find the net electric field at that point.
So that crucial tip about signs must apply here too, right? When using E equals KQ over R squared, don't plug in the sign of Q.
Exactly the same principle. Calculate the magnitude of the field using the formula, E equals KQR2. Then determine the direction based on whether Q is positive, field points away, or negative, field points towards. Draw it. Then do the vector addition based on your chosen coordinate system.
Magnitude first, direction conceptually, away from plus A towards rec, then vector sum. That consistent approach seems key.
It really is. It builds understanding of the physics, not just formula plugging. It helps you avoid those sign errors, especially in 2D problems where directions get complex. Nail down that method.
Okay, wow. That's a lot of ground covered. We went from the basic idea of charge and its conservation
Can't be created or destroyed, only moved.
to Coulomb's law, describing the force between charges, that inverse square relationship.
And how to calculate that force carefully with directions.
And finally, to the idea of electric fields, the influence charges have on a space around them, how we draw them and calculate their strength.
And how they all tie together. The field tells you the force per unit charge. The force depends on the charges and the distance via Coulomb's law.
It all forms the foundation of electrostatics.
Absolutely foundational. For grade 12 physics, for the NSC exams, this stuff is crucial. Get this solid, and topics like circuits, capacitors, electromagnetism later on, they just make so much more sense.
It really builds the base.
It does.
Yeah.
It's like laying the right foundation for a house. Get this right, and the rest stands strong.
So the big takeaway from this simple science summary: practice seems essential. Drawing field diagrams, solving those force and field problems.
Yes. And really focus on that conceptual approach to direction we talked about. Don't rely on formula signs for direction. Figure it out with attraction repulsion or the positive test charge idea. That's a skill that pays off.
Definitely. Practice those skills. Nail down that method.
For sure. And maybe a final thought to leave you with. We've talked about electric charges interacting through these invisible fields and how gravity works similarly between masses with an inverse square law field.
Yeah.
Well, what other fundamental forces are out there? Do they also work through unseen fields of influence? What does this concept of action at a distance via fields tell us about, well, the fundamental nature of reality itself?
Fields everywhere. That's definitely something to chew on. Thanks for breaking down electrostatics with us today.
My pleasure. Keep practicing those problems.